Yeah, well, really, I got started in the HCI business because as a young kid, I was a rock and roller, and my band had just broken up, and I thought, well, I got to buy some time here, so I'll go into electrical engineering or something. And the college was full. That was in 1980 or something, and someone said, well, you could go into arts and science and take this computer stuff. And I thought, well, Elvis Costello, who was a musician, maybe some of you remember, I think he did something like that. So I got into computer science. Then after I finished my bachelor's, I sort of realized that computers are sort of weird and super hard to use, and why aren't they more like musical instruments? And it seems like I'd spend 8 hours a day in front of the computer, I wouldn't really learn anything. Whereas if you practice for 8 hours a day, you'd be a pretty skilled musician. So that always sort of stuck with me, and eventually I ended up going to University of Toronto to do a master's and hooked up with Bill Buxton, and kind of a funny story there. I wrote a letter to Bill saying I wanted to go there and study with him, and he wrote me back and said, no, you should go someplace else and study with somebody else. But I went there anyway because I thought he seemed like a good guy to work with. And anyway, so that's how I got into the HCI business with this sort of notion that computers should sort of fundamentally be these sort of skill-driven things that you could build up your skills. Along the way, I did a bunch of research on this radial menu technique called marking menus, which lots of people use and stuff like that. That ended up in the products that this company called Alias used. Alias got bought by Autodesk, and then I arrived here tonight. So that's sort of my background. Now I do a little bit more than just research on menu systems. There's a breadth of research that goes on within Autodesk, and I'm the head of Autodesk research. And throughout this talk, you'll sort of get a flavor of it, but you'll see it's gone sort of beyond, beyond sort of the glass of working at sort of the user interface GUI level. And I included this slide because I thought, well, I think we're at a really interesting time. People always say that at the beginning of talks, but to some extent, this is actually true that we've got the situation, and Toronto is kind of unique because it's such a stronghold for user interface stuff. I didn't know that when I arrived here, and you sort of have to pinch yourself every once in a while to realize that, like the University of Toronto, that community there is like one of the top UI, top publishing places in the world. So there's sort of that culture there. Toronto is uniquely this combination of all these different cultures and stuff. So there's a lot of stuff going on. There's a lot of building going on. I like the fact that there's cranes being shown here. So people are building stuff. There's electricity, and basically the world is digitizing itself. And the old days of, the user interface being the thing behind the glass and maybe a mouse and keyboard, that's all going to radically change, right, with the Internet of Things. So suddenly you have this combination of the built world and the virtual world meeting. And we're no longer designing interactions, but we're designing the entire experience. And hopefully through this talk, I will convince you that what we're thinking of experience now is actually pretty limited. So the good news is that we will be gainfully employed for a long time working on that. And I think it'll be more rewarding than just making icons that people can guess what their meaning is. So I'm going to talk about building stuff, making. And what do I mean by building stuff? And really, we sort of joke within our research group. It's like, well, it's anything that God didn't create, so anything sort of man-made. Throughout this talk, you're eventually going to find out that's actually no longer the case. And that's where building stuff is going. Now, I work at Autodesk, and so for you guys in the audience who are familiar with Autodesk, we sort of think of our tools, computer-aided design tools, as being involved in the process of pretty much anything that's being built nowadays. And if you're not using a computer to design and build something now, probably in the future you will be. So that's a very clear trend. And you can see it spans the entire range of things from the original drawing, doing draftsmanship type of work, to doing special effects in movies, to designing actual plants and cities and planets and stuff like that. So it's a very, very, very broad field. Okay, so let me talk a little bit about the future and really why I think this is going to be a pretty dramatic effect. So if you look back at the computer industry, and this is sort of what my argument is going to be based on, the key thing that the computer industry did is they built systems to build systems. So you can see in this picture here is a picture of an old computer, and those were sort of hand-wired, manually made systems. But of course, the integrated circuit changed all that. It was a way to miniaturize those things, so it made them small. But the key thing, it was a way to digitize that process of making things. So now when you buy a computer, no one actually manually links out the transistors that are on a chip. There's various tools that allow you to do those things. And there's tools that use other tools. And so it's a highly digitized, highly tooled process that's abstract. A large part of it is completely abstracted away from the user. And that's what's going to happen in the physical realm. And we see that happening fairly rapidly. So the key understanding here is to program the physical world in the same manner we program the virtual world. So that's the trick, because programming in the virtual world has all these nice properties that you can modify, you can undo, you can do versioning. And so if we could do the same in the physical world, which we do to some extent in the physical world, but if we can do that with the same sort of agility that we do in the digital world, we have a big advantage there. So here's a typical example. So in the good old days, if I was going to make this pencil maker, it's pretty straightforward, right? First you obtain the materials, the piece of wood. Then you obtain the drill bit, and then you drill the 1/4-inch holes in the holes where you want the pencils, and you're done. But here's a pencil maker that I made just recently, or that someone in our group made just recently. And that was a pretty different process. She designed it on the computer first, sort of sized up her pencils, decided the shape that she wanted, and then 3D printed it. So that's a very different process than sort of the manual building of things. So that's all pretty simple stuff, but the thing I think the key things to realize is the change in the process really changes some fundamental things. It changes who's doing it, how they're doing it. Because remember, like in the wood example, although it's a simple example, there's a bunch of subtleties. If you choose the wrong piece of wood, you choose some super hardwood, you'll have a hell of a time drilling it. So there's a lot of material knowledge and craftsmanship knowledge that goes even to making that simple little pencil holder. So the how is really important. And the who changes because you don't have to be a person that has a wood shop, or you don't have to be a wood craftsman, etc., etc. And also what you can actually build can change. That pencil holder that she built has electronic sensors in it that sort of sense which pencil she takes in and out for her. And of course, where you build it changes. So you can, in the comfort of your living room, 3D print something. The point is that those subtle changes in the fabrication process change a lot of fundamentals. So what are the key ingredients to this change? I just said 3D printing. The other key ingredient, it changes what is buildable. Things that were previously unbuildable to you, that person, now become the buildable things. And fundamentally, and I'm going to show some examples and argue, that it's going to change the way we design things in sort of a very fundamental way. So 3D printing. So probably all of you are aware of, for 3D printing, and you've seen examples of it. And sort of the hype and the holy grail is like, oh yeah, I would buy something on Amazon and then just press print, and then my watch would come out, and then I have a watch. That's the promise of 3D printing. It'll take a while before we get there. There's a lot of challenges along the way. Really, our sort of theory within Autodesk is that the consumer side of 3D printing is sort of overhyped. When we asked our CEO, Carl Bass, who's a real maker and a craftsman, he kind of says, yeah, I use the 3D, he has a 3D printer in his shop, and he says, yeah, I use it a little bit less than my toaster, sort of thing. So it's not, he hasn't thrown away all of his woodworking machines and his metalworking machines and stuff like that. And so if you're making small plastic parts and stuff like that, it's a great time to be alive in that sort of thing. If you're making more complicated stuff, that stuff will eventually come, but it's not going to come all that fast. So there are some people that think that 3D printers are sort of a moniker of a coming revolution in manufacturing, right? That suddenly our manufacturing lines that use machines or robots are all going to be replaced by 3D printers that print out very quickly cars or things like that. That sort of remains to be seen. I think the big challenge there is that manufacturing is a very refined process, right? And so you have to beat those existing processes of mold making, sheet metal forming, and stuff like that. So we don't really know what the answer is going to be. We don't know what the answer is going to be yet. But however, you can do some great stuff with 3D printing. The main thing is that complexity really changes the equation. So some parts that were normally very complicated things to do now become as simple as doing a very simple part. So that bowl, for example, if you were to manufacture that with using traditional methods, you'd have a hell of a challenge to actually do that. But once you have the virtual model of it, you just simply print it out. And it prints out in the same time that if you print out a simple shape bowl. So 3D printing has those really nice attributes. And you can see that you can do these shapes which are pretty much unformable in sort of any other medium. And finally, the image in the corner shows like a set of speakers where it's 3D printed and with sort of fundamental attachments to add in lights and speakers and stuff like that. So there's a whole bunch of things that you can sort of encompass in the design that normally would happen at a different spot in the manufacturing process. The other thing is that what we're finding out is it's really interesting that 3D printing processes, while they're sometimes being used to replace traditional ways of manufacturing things, some of the real rich spots are where they're creating parts that can only be 3D printed. The only way they could exist to be 3D printed. And this is this little part that we have in our lab, which is a set of gears, and it's printed out as a set of gears. So if someone separated those sets of gears from one another, you can't actually assemble it together. They actually need to be printed as one single set. And so 3D printing allows things like that. The interesting thing, and a story that I just recently heard from a jet engine manufacturer, is they said that they've discovered, it's sort of non-intuitive, that using 3D metal printing, they can print out working versions of their jet nozzles and test them and get them done, like get them sufficiently tested so that they're ready to go into an aircraft before someone can design them in the traditional materials digitally, run all the virtual simulations on them, and then actually get a part out. So there are things that can only be 3D printed, and because of that, it turns out to be a faster and better part. So there's sweet spots along the way that we didn't even realize were possible. So here's just another example of this. So right now, 3D printers generally generate sort of single material prints, but you can do a lot of really clever and nice things once you start to print multi-materials. And that's sort of the next generation. Like upstairs, we have a multi-material printer that can sort of do types of stuff like this. And what's really interesting about these things is that you can print things that have certain textures in them to get certain behaviors out of the material. So if you want something that flexes a lot in one direction and very little in another direction, you can program that in the material by just having a soft material at certain spots. The most interesting thing is, like, unlike other materials, like you could say, well, I have a sheet of plywood, it's flexible in one direction and it's stiff in the other direction. But we can do any sort of arbitrary pattern. So you can get things that conform to your body, or conform to odd shapes. So it opens up a bunch of functionality of the materials that were really never available before, and certainly weren't as programmable before. So that's a lot of hype about 3D printing. I mean, there's still tons of issues. And in Autodesk, we know lots about these because we're actually shipping our own 3D printer now. There's a strength of the material. Can we produce things that are strong enough? The cost of printing, right? It's expensive to print things. That's one of the reasons why people don't use them for manufacturing nowadays. There's the reliability of the printing process. I don't know if any of you, does anybody here have a 3D printer like a MakerBot or anything like that? Yeah, so it's like, hey, sometimes your print that doesn't work out. There's all sorts of subtle things, even with the plastic and the really reliable ones. There's definitely the size. Most people are printing small things. We need to manufacture big things. There's the speed. It takes a long time to sort of do these things. There's the overall quality of them. And there's also a question of whether it's toxic or not. We just found out the other day we wanted to do something and it gets cut out of styrene plastic, and we can't do that with a laser cutter because it produces toxic fumes and the venue won't allow toxic fumes. You know, go figure. So anyway, so there's long ways to go within 3D printing. However, there's a lot of great progress, and especially on the industrial side. And this is the work of a company that we just recently acquired. And I think it's really good examples of the really subtle things of 3D printing. So in the upper left-hand side is a 3D printed part, but it's a part for your body when you get a hip replacement. And the interesting thing about that is that it fits into the ball where your hip would normally go. And that pattern is a specially developed three-dimensional pattern, sort of a lattice of interconnected parts. And the bone readily grows and attaches to. So it becomes a stronger than bone attachment to your body. And so those things are actually just things that people arrive at after experimenting with these things. Very difficult to manufacture in any other way. Actually, fairly difficult to manufacture in metal too, but that's what they do. And the other examples are sort of what you typically think in terms of lightweighting parts. You can make the things on the insides of the parts, but you can't mill out, or you can't sort of burn out. You can make those porous to some degree, but still have really high structural things. So in a way, 3D printing will allow these sort of super materials to be created in the future. So I don't want to get carried away and sort of think, oh, well, if I get a 3D printer, I'm done. We sort of found out that if you actually fabricate something, and any of you people out there who build stuff, you realize the 3D printing part is just a small part of a larger process of actually fabricating stuff like this. So Autodesk, I think, did a really cool thing over a year ago now, where we decided we were going to rent some office space and start a fabrication space. Initially started where we could put our 3D printers, because we were experimenting with that, and where we could support some of the people who were doing fabrication projects. And that really ballooned into this really beautiful maker shop. Did you have a question?
Yes. Is that accessible by the public? Like, is that kind of like a tech shop kind of concept?
No, it's not open to the public like tech shop. The reason it's not open to the public is because people can go to tech shop to do stuff like that. We don't want to assume the liability, so it's it's for our use only, right? But actually, we're an investor in tech shop, so I would encourage you to go to tech shop. It's a very sort of similar thing. And tech shop, actually, it's a great question, because when we talked to the president of tech shop when we were planning this, he right away said, look, you guys, you have to include, you can't just have just printers and a wood shop. You need a metal shop. You need all the stuff. Someone needs to take a project from beginning to end. Otherwise, sort of why bother? And so my main message here is that, yeah, you need a lot of extra tools to get a project done, but a lot more of these are sort of the traditional digital tools, like we have CNC machines and water cutters, all computer-guided stuff too. So you can see how the digital manufacturing process, or digital control over manufacturing, is being combined with sort of traditional tools. And you'll get more and more digital stuff over time, because that's the trends that we see. Like if you want to cut a piece of metal and it has to be accurate, you can either cut it by hand and maybe grind it down, or you can take it to the water cutter and an AutoCAD specify a profile and have it cut it out. So that's a real clear trend. So I just wanted to give you a sense that it's really an array of computerized machines that are going to sort of really change how fabrication is done in the future. So we can print a lot of other things. Probably most importantly, we can now print carbon fiber. There's a picture of a prototype of a carbon fiber printer. And people are even experimenting with printing much larger things, like printing houses with liquid cement and just pouring things. And those are all pretty reasonable, understandable things to do. The carbon fiber one is especially fascinating because you can do things like print things in lightweight plastic that are fairly strong and then wrap it in carbon fiber so it's super strong. So we're doing some stuff where we have motorcycle parts that are like 1/10 of the weight of the aluminum part and twice as strong. So there's a lot of really interesting stuff going on in 3D printing. And it seems like every day we see some sort of startup trying to do stuff like this. So that's actually sort of the understandable, boring part of this. The really interesting thing is when you start to look in general, and what is programmable? What things could we program out there? And so if you start to draw a chart, what could we digitally control and fabricate with? So on one hand, if you look at things that are small and things that are large, they're on the right-hand side. I guess on your left-hand side, sorry. You think of the components that we traditionally build stuff out of, bricks, lumber, steel parts, integrated circuits, chips, and stuff like that. And those we assemble into the more traditional things in manufacturing, buildings, vehicles, etc., PCs, stuff like that. We assemble those into cities and factories, etc. At the bottom end of the scale, the very small things that we build those components out of it's really the world of material science. What are the alloys, the plastics, the nanotechnology, and the MEMS technology that we can use. So that's sort of, the well-understood and well-oiled world of manufacturing. That's the non-organic world, right? We sort of think of that is the dead world. You can also do the same analysis for the organic world. So at the very bottom level, you have the things that life is built out of, DNA, viruses, and bacteria. Small things like that. Those get assembled into cells and tissues. Those get assembled into organs and limbs and organisms, and then in environments and ecologies. So the interesting thing that I find really fascinating is that, as you get into sort of the middle lower part, those things all smush together, because you can do sort of structural stuff with DNA, or at sort of this small enough level, actual materials affect the way cells operate within the body. And all those things are potentially things that you can program and make stuff out of. This is not any sort of new insight. People looking at sort of the future of biology have been saying this for many, many years. And really what they're saying is biology is can be a predictable and programmable thing to build stuff out of. Someone once explained it to me, it's like, and if you read this book, you'll find out, like in the old days of biology, they would just have stories about, well, if we combine these certain chemicals, we'll get yeast cells to grow at this rate. But now they have, for a lot of these things, they have measurable, predictable, reproducible, engineerable, and therefore programmable stories or tables about the way these things work. And I'll show you some examples of those. It's sort of like, if you think of the beginning of aviation, when the Wright brothers and others were first trying to fly, initially they had stories about, well, we know if we make the air surface slightly curved, we seem to get lift from that, right? Nowadays, there's actual computer programs that'll tell you precisely what lift you'll get with that airfoil, right? So those things have become completely engineerable and predictable building blocks within that fabrication discipline. So here's a kind of interesting example, right, that sort of cuts across these things. So we did work with a company in California called Organovo, and they're looking at 3D printing of living cells. Now it turns out this is astoundingly simple, right? You get a 3D printer, you get a needle and syringe, you get some cells, you put them in some fluid, and you go around and you drop cells down onto some medium in which the cells will grow. So they got a lot of press over this, and it's like super cool work because they can make press headlines like, you can print human organs and stuff like this. That's all true. The limitations right now is that if you try and print, let's say, a liver, which would be a good thing to print, right? They can print out the liver cells, but they need the blood capillaries and the vessels and all the structures. So we don't quite have that part of it figured out yet. But the real value of this stuff is in generating sensors where we can do drug testing, for example, against tissues that have liver cells in it. So if you're doing, let's say, if you need a drug and they need to test it against your liver specifically, they can take some of your cells, reproduce them, and then make a small microchip, and that can be used as a sensor to test how effective a particular drug would be against your liver before blasting it into your body. So here's another example, some work that we were involved in, and it's super relevant to tell the story to this group of people. So I guess it was like about 4 years ago, we went to the Wyss Institute in Boston which does some of the sort of the top synthetic biology work in the world. And we were talking to some of their scientists there, and they had been using one of our software tools, Maya, which is designed for making animations for Hollywood. And they had been using it for our project. And one of the scientists said, "Oh, it's so great you guys are here because we're like doing this project where we're building these small DNA robots that go into your bloodstream and kill cancer. But Maya is really hard to use for us, so could you make something that's simpler?" And I remember this, wait a minute, you guys can harness DNA to kill cancer, and you can't figure out how to use Maya? It's like, okay, we can help you, you know, sort of thing. But that actually was the real truth. And so I'll tell you what they were doing. And so it's this sort of incredible blend that shows that you really need good tools up front to harness some of this stuff. So first I'll tell you about the technology that they were using. So what they do is they're able to program strands of DNA such that the DNA, when they create it, will self-assemble itself into a particular structure. So they can do something like they can make DNA so that two pieces of the DNA will just connect itself together. So that's a very simple example. And that's what DNA does, right? So it has these little sticky bits and floats against one another and they hook themselves together. But using a fairly sophisticated algorithms and tools, they can actually make little physical structures out of them, like L shapes, little spheres, and little cones. So what you're seeing on the left side there is really this a collection of DNA that has this clamshell sort of shape and function. So it's like a little compartment that opens up. And at the end of it are these little things that are called keys. And those keys fit the geometry that's on the outside of a particular cancer cell. And so when that little nanorobot, as it's called, because it's very small, much smaller than like a white blood cell, when it floats around in your bloodstream and comes in contact with the cancerous cell and its geometry matches the key, that little clamshell opens up. And the cool thing is what they do is they put these enzymes that naturally occur in your body that tell cells to shut themselves off. And so it works out really nicely. So they have this programmable medicine that they can target certain cancers on because the geometry of the cancer's cells change. And so they can change the shape of the key. So they can address different types of cancers. And in order to kill the cancer, it just naturally tells the cell, okay, shut yourself off, which is what the cell's not doing in the first place. So the cell sort of gets put right back on the right track. Because normally, any cell in your body that sort of goes a bit crazy, under normal conditions, the body just sends these little purple guys in and says, okay, shut yourself off. So we were thrilled because I thought, well, how did I go from making menus to working on cures for cancers with nanorobots and stuff like that? So it was really cool. And these guys needed our help to build better tools because essentially they're building these really small little structures. So all that stuff is sort of related at the bottom of the graph. I think that's the really interesting news. Now, you're probably saying, Gord, why isn't cancer cured? It looks like Sean figured it out, right? Sean and George figured it out. Yeah, so when we met them back then, they in theory had this stuff going. And I go to the next slide. And so that's what they initially showed us. It's like, oh, we're using Maya, we're programming this stuff. And so we wrote them some better tools. Like, we can do that really, really well. And in the meantime, they had already generated the sequences for the DNA. So basically, you go up here and you select prints. It prints out a file, an Excel spreadsheet of the DNA sequence that you needed. You send it off to a DNA sequencing shop. They send you back the DNA. You put it in a test tube. You heat it up. You shake it. You look under the electron microscope, and lo and behold, you have these little rectangular structures appearing. So several months went by. We went back to them. They were testing the little nanorobots in a petri dish against cancer cells, and they were killing cancer cells. So it's like, holy smokes, that's super cool. So currently they're on to the next step. And last time I checked with Sean, the challenges are, there's sort of two challenges. One is that you need a lot of these little nanorobots. So they need to synthesize a lot of DNA. So they need some way to manufacture them. And you can do that using DNA. So they're going to have to do something like that. Then the other thing is that the liver kills these little guys. It squashes them, which they were sort of surprised by. So now they've got to figure out, maybe there's some structure that they add on to the liver or some molecule that tells the liver, okay, these guys are friends, not foes. But that's a great example of sort of where digital design is headed, into these very sort of exotic areas of personalized drugs and things that we never thought we would be there. So I'll just give you a little bit more evidence of this. So this is a biology conference. And basically what's happening at this biology conference is people are sort of going through lots of different processes in biology and saying, which one of these things are very engineerable, reproducible things? Essentially what they're building is sort of a cookbook of, these are the things that we can reliably do. These can be the building blocks to build more and more things out of it. So much so that they talk about creating new parts and new devices. And here's somebody who made, as you can see, smiley faces out of DNA. So that was sort of the warm-up task of doing the nanorobots. So if you look at what's happening in this area, it sort of reminds you of the early days of the PC world, where you saw people sort of homebrewing computers, and some students would have some Apple II in their dorm, and they'd be sort of fiddling around with it and stuff like that. This is a picture of well, first it's a newsletter from the old Homebrew Computer Club, and some of us who are older might remember those days. And the other one is the Homebrew Synthetic Biology Lab that some student has in their dorm room. So, I mean, it's really interesting. Like I was talking to one young guy who's in our research group, and his side project is like, oh yeah, I'm actually trying to develop this, is it a yeast or a lichen? I think it's a yeast that eats radioactive material. So I thought, well, that could be very useful. We could use something like that. So people are they're experimenting with stuff just in the same way that we wrote programs back in the old days of early PC days. So here's another indicator of that. So this is a synthetic biology competition that's held at MIT every year. And it's a combination of some university students and a whole bunch of high school students who are sort of routinely doing stuff like this. Like when I was there, one of the winning teams had this nice little demo where they had programmed this bacteria, which normally sort of travels in a straight line, and they had genetically changed it. So if you shine a light on it, it'll make a left turn. And so it's like a high school class project. This stuff is very controllable and very programmable. So that's on the living side. On the sort of the non-living side, there's lots of people experimenting what's called 4D printing. And really that's just the concept. When you print something, you take it out of the printer, it'll develop and change over time. And if I could play the videos, this is a tool that we've been developing in our research lab, and it just runs a simulation. So we've been printing out these material strips that when immersed in water causes different parts of the part to expand and shrink. So we can get parts that, once you take them out, they're straight, and you put them in water, and they change in shape. And so in some ways, it's very similar to DNA, which has all these strange folding properties and stuff like that. So there's the simulation of what we think if we print that material out, the way it should bend. So it's sort of supposed to form itself into a cube. And this is the real thing being thrown into a tank of water. This is done with some of our research partners at MIT. And if you fast forward, it doesn't happen fast. 75x speed forward. So eventually it pulls itself into the corresponding shape. So the main point is that we can program that stuff. Some kid can go in there and program that into. We can create tools where you can have things that fold up over time. So as long as it's digitally controllable, it opens up all these really interesting avenues. So okay, so that's on the material side, right? Did you have another question?
Yeah, is that, when you said that 4D printing is controllable, does it also imply that it's predictable?
Yes, yeah.
So could you apply that to, say, like enzyme folding?
Yeah, if you have the predictability algorithm, right? So, like, that's one of the things with enzyme folding and other life sciences folding. There's tons of people researching that to figure out, okay, what is the algorithm? Can we predict the folding, sort of thing? In that case, we can predict the folding because we know a little bit of the shrinkable material here and a little bit less there will cause it to collapse, right? Or to cause it to bend into a certain shape.
Right. So
Whereas,
proteins.
right. And so with the DNA's example, what they're doing now is they'll have strands of DNA, and the most important parts are the staple connections. That's where sort of DNA is most likely to stick together. And so that's not really folding, but it's more the attachment. So they've sort of figured out sort of what controls that behavior. But you have to know that, right? There's no software that, we have to do research to figure out what those things are for the different materials, right? Yeah, sure.
And of course the folding and the actual structures are not dependent on temperature. It's the actual contact with the water molecules, and it's not, because like materials in essence, like they expand and they contract by temperature, right? So it's I'm just assuming that it's the actual contact with the molecules and not the temperature change that makes the
in this particular example, it's a hydro-based material, right?
Okay.
But at sort of the molecular level, everything sort of depends on temperature and stuff like that. Yeah. So that's sort of the trick to all these things. They're still governed by
Natural laws.
yeah, the natural laws and stuff like that. The funny thing about this stuff too is that at the smallest level, the basic laws of physics, as we sort of know them in sort of the Newtonian sort of way, they don't really apply. Like, to fully explain that DNA example, you have billions of strands of DNA all bouncing around, and as you heat it up more, they bounce around more, and then a few of them hit and attach in the way that you had planned. And so, if we would have looked at all the DNA produced underneath a microscope, it would have been a yield rate of like 10% of them are the nanorobots that we need. And the rest of them are these malformed things, right? But 10% is good enough. 10%, we do it just 10 times more than what we need. We got it, we put it in somebody's blood, and we're done. And sort of that's the way that biology works, too. Well, that is the way biology works. Okay, so let me talk about a little bit more on the tool on the tool side. So probably most of you realize that CAD stands for Computer-Aided Design. We sort of joke that, really it's actually more computer-aided documentation. And it's good. Autodesk is a $2 billion business based on that, and it's very, very useful. But you can sort of think of it as like, well, actually, really what it is that once we've got the design all figured out, we write it down, we draft it out, and we give it to somebody to manufacture it, right? And so, like, we don't really, it's more like computer-aided drafting. Even though, on the upper right-hand side there is a screenshot from our, manufacturing product inventor. So you can do really sophisticated things in these products. But it's not clear really how much the computer is aiding you in the design. You're doing a lot of the groundwork. You're sort of figuring everything out and then drawing it. Now, when you think about design in a very general sense, you really just have the requirements for the thing that you want to design. And I'll go through this example to show you what I mean by that. Suppose you wanted to design this fan. Let's say it's a fan for an air conditioner. And just to simplify things, we say, well, given the power output of our electric motor, we want an airflow that's greater than this number, and we want it to be quieter than this decibel level, right? So those are sort of the requirements for it. And so using our existing tools, what a designer or engineer would do is they would design a fan like that. They could run simulations on it, find out what its performance is, and decide, yeah, does it meet the criteria? And if it does, you're done, right? And actually, if they have more time, and designers always sort of, or people who work professional, and you guys design stuff too, it's like, well, we just keep on designing till either we run out of time or we run out of money. But if you had a little bit more time, you could probably do 2 of these and pick the better one out of the 2, right? But you know, if you think about it, really, you just really have these goals. You want to maximize airflow. That would be the best thing. You want to minimize the amount of sound that comes off of it, given the constraints of the context. It has to fit on a 1/4-inch shaft, fit in a 4-inch cube space, etc. So this, where I'm headed to, is this notion of goal-driven design. And this is what we're looking at right now. And it's very different than the kind of design that we're used to. And the kind of design that we're used to is actually very strange in a way. Because it's very odd, especially if you think of this fan example, that if you were to design this now, you start with the shape first. You get into the tool and you start drawing the shape. But you actually don't care what the shape of the fan is, do you? You care that it has this amount of airflow and that it's actually a very quiet fan. And so those are the goals. So it's not geometry-driven, it's not shape-driven design, it's goal-driven design. And so goal-driven design looks like this. The user inputs not the shape of the thing, but the goals and the constraints of the situation. The computer then somehow automatically generates the design, and then the computer would test if the design meets the criteria, meets the goals. So I'll walk you through this example. You probably figured it out. So using this technique, we could generate 3 designs, let's say, and pick the best of it. But since the computer does it automatically, we could generate several dozen and pick the best out of the dozen, right? Now, since it's a computer and you had a more powerful one, we could do it for hundreds of these, right? And then the real kicker to this, as we start to take our computing from the desktop to the cloud, is we basically have infinite computing power available. So we can generate not hundreds of designs, but millions of designs. Now the computer tests each one and find out which one is the best one. And then you actually find out what is the optimal design. You basically make a graph of performance, and you find the thing that's right on the knee. And so that's the real promise of these new design tools. So, but there's some major challenges. I mean, first there's sort of the psychological hurdles, like, well, what do you mean I don't design the shape, sort of thing. So that's really like, how do you express the goals? And once you get into a design, you realize, oh, guess what? When I'm designing the shape, I'm actually expressing a bunch of goals in a certain way. Maybe some of the goals you don't want, but that's a way to, in bulk, express a lot of the goals. So that's sort of one of the problems. The upside is that once you express the goals, you have them expressed. Whereas if I give you the fan, and I say, make a variation of this fan, you actually don't know what the goals of that fan were. You just know the shape. So there's sort of this vagueness in every design and in any design discipline. When someone gives you a design and they don't tell you the goal of it, you're like, oh, I guess your goal, did you put this here because you wanted more airflow? And it's the same thing within user interface. You really need to understand the goals, right? Okay, so then the second challenge is, well, how do you automatically generate these designs? Now, people who work in this area, I mean, it's sort of astounding when they do, for example, when they build airfoil, when the structure that goes into the airfoil for a jet liner, they pretty much do these things where they create a volume and then they randomly drill into it each time with the computer testing whether it'll actually support the stresses that are going to happen to the wing. So because you have infinite computing power available to you, or close to infinite, you can do so many of these that eventually you come up with some shape. You've drilled with some pattern of holes in this thing, which somehow meets all the goals. It's super light. You drilled a bunch of holes in it, so it's super light, so it meets that goal. And it's super strong because you've taken away all the material that you don't need, right? And the computer just found that one. So essentially, we're taking the design problem and mapping it into a computer search problem. And Google was very successful in taking the information problem and turning it into a searching problem. And then the final problem is, well, once you get it, how do you evaluate all these things? So I don't think we can input the design goals for a jet airliner tomorrow, right? But I do know we can input the goals for basic angle brackets and stuff that you shouldn't be designing the shape for, right? Because like if you look at the humble angle bracket, which occurs in so many places, it's very simple. It has certain shear forces and load forces and stuff like that. It's these types of things we can probably express the goals for their performance and automatically design them. So all that stuff that you used to design in or use parts, the computer will just figure all that stuff out for you. So you'll just say, oh, I want a car frame and I need to attach the wheels here. It'll figure out how to attach the wheels and stuff like that. It'll do a lot. It'll do some computer-aided design for you. So we're building stuff like this in our lab. And so here's an interesting example. I mean, the computer does strange things, right? And this is what's really exciting about it. So this is a part that's going to go on a spacecraft that's going to the moon as part of the Moon Express competition. And this part just holds on one of the little thruster rockets onto the side of the body of the spacecraft. The spacecraft is just this little donut thing. It's basically all gas tank with this little platform on top where you put whatever payload you want. And so that's all this little angle bracket has to do is withstand whatever lateral forces, etc. forces that happen to it, because the little rocket part goes on here. This piece is actually only about this big. And this part just attaches to the tank. And so we input those goals into the computers and the constraints and the different types of materials and material properties that it could be built out of. And it came up with this. So you can see it just whittled away the space to get some sort of minimal thing. And that's what we find is really exciting about this. And when we showed it to people, structural engineers, they sort of say two things. It's like, well, I would have never designed that myself. And like, how the hell do I test that sort of thing? So we got a long ways to go on this stuff, right? But this is just an inkling that you get into this design space where the computer is really actually aiding in the design and coming up with new stuff that you probably never thought about. So here's another example. And when we show this stuff to designers, a lot of designers say, well, it's not going to take me out of the equation. I'm going to be unemployed. You know, this program is going to do all my work. I actually think the complete opposite is going to happen. So here's a classic example where we had a designer design the shape of this bicycle frame. And we basically said, like, make it as ungodly cool as you like, you know, something that would really, really sell. And then we'll let our algorithm figure out a structure within that envelope of shape for the frame that will withstand the forces for the bike. And if you look a little bit closer at this, it comes up with this crazy lattice work, right? And you, of course, would never build that. You might build something with a whole bunch of struts and stuff like that. The point is that, you know, we can imagine the system easily doing stuff like, as you change the shape, it just completely reprograms all the lattices and stuff like that. So it actually frees up the designer to be more expressive and also frees them up to understand the true goals of their design, because you think, like, why did the computer do that? Well, it turns out, you know, we have the over-constrained problem or under-constrained problem. So it really is a different and experimental space to get into. Okay, so hopefully I've talked a little bit about the future of making and convince you that 3D printing really leads to fully digital fabrication and why that's important. The notion of what is buildable is really going to change and is sort of changing in front of us. And it's not following any rules of like, well, this is the manufacturing sector and this is biology and they don't meet. Those two are going to meet and interact like crazy. And finally, the way we design things is pretty much going to have to change to harness all this stuff. And so those are the three basic tenets of the talk. So the last closing note is that, well, you know, if you're going to build something, like, let's do something really great, right? Because it's sort of an opportunity. I always look, this is a box top from some old Meccano set for this. Us old guys remember those. That's how you sort of build stuff. And it's really about sort of the joy of building stuff. And, you know, the real joy of building, I think, comes from solving some really gnarly problems, too. So I just thought I'd show these final examples of stuff that I really admire. This is Sean Reese, the guy that we worked with the cancer nanobot killers. This is Matt Ratto and Matt Ratto from the University of Toronto and Ryan Schnitt from our research lab. They're working on a low-cost 3D printing process for printing prosthetics for kids in Uganda who've lost their limbs due to stepping on mines and stuff like that. It turns out that you can do 3D scanning of the limbs, so you can get really good fitting prosthetics and print them out on really cheap printers. So we just love stuff like that because, like, talk about having impact, right? One day the kid's like not walking, the next day he is. And so in the end of October, they're going over to Uganda to get people set up there with 3D printers and start printing these things. So there's just a lot of great stuff you can do, and that's clearly a completely digital process. And there's Azam Khan, who's still here in the back, who's sort of looking at this internet things of how we can sensorize the world and digitize the information that we have about buildings and how buildings perform to make buildings consume less energy and therefore produce less carbon gases and therefore slow down global warming. Turns out in a lot of places the major cause of global warming is heating buildings, and it's not heating new buildings, it's heating the old buildings. So it's not like we can build new buildings and we're all saved. We've got to do something about the existing buildings. So we think by basically digitizing that world and getting that information, we can do a lot of optimizations on it. And then finally, you know, another real classic example is just sustainable energy technology, like current run turbofans. So that's the end of my talk. We have this website if you want to learn more about some of these projects and stuff like this. And super pleased you guys could come to Autodesk tonight, and I'm happy to answer some more questions.
Questions? We'll take questions from you.
Sure.
Question, like for example, I was looking into like just home 3D printers, like for example MakerBots, and since it's relatively, like let's just say we're trying to build an ashtray, right? And you're not actually, like from what I understood is instead of actually printing layer and layer and layer and just filling up the whole ashtray, what they would do is they have like this honeycomb sort of structure inside, right? Just so that it fills it up, gives it some sort of sense of it being like hard.
Yeah.
But without wasting, let's just say, the actual plastic involved. I was just wondering, are there any like softwares that would optimize the structure, like how you were saying that it would optimize the structure and the strength of the material just by the patterns, like automatically just generate like a honeycomb structure which would optimize the strength of the ashtray, for example?
There are some, but that's a direction that these tools are going to have to go in.
Okay.
Because there's a great question, because it brings up this really important thing, is that if you look at the way CAD tools work now, we're really good at sort of designing the outside of things, right? Even though you sort of work with volumes and stuff like that. But if you design something like, we always think of the classic example, if you take an apple, you want to design an apple, and the insides of an apple, oh, how do you do that with a CAD tool? I got to make these things inside. It really doesn't work. And so what you're talking about is like, how do I do structures on the insides of things and stuff like that. Now the 3D print manufacturers have their own algorithms that when you put your data in, it'll do the simple honeycomb pattern and stuff like that. But those are pretty basic, and they're pretty dependent on the particular material that you're going to use, right? That's why they're in the printer. But we think that stuff's going to migrate out of the printer, or it may stay in the printer. I don't know, but whatever the case, that'll become much more sophisticated. And in our lab, like we have, there's this thing that when you print something, it may need support depending on what you printed on. Like if you have an arm out here, the plastic is still soft and it'll sag. So there's this question of how you do support material. So they'll put support material going down. And so there's pretty simple ways of doing it that a lot of people are doing it now. There's very sophisticated ways that give you a lot of properties that you would like to minimize warpage and twist and turn and stuff like that. So all that stuff is going to be super relevant in 3D printing and 3D printing in metals and all that stuff. That's all stuff to be figured out.
Can I ask another question? I'm sorry.
Mark? Go ahead.
Okay.
Oh my God, sorry, I got chosen. You
I thought I was chosen.
Fascinating high-end examples, and you kind of mentioned that maybe consumer
versions are not where the action's going to be, at least initially. I kind of guess if you use the analogy of like the personal computing revolution, and maybe it was like the Apple II that really made things take off. Well, do you think there's ever going to be an Apple II for maker technology where it democratizes it and a lot of people can get involved and start building software and tools on top of it? Or are we at a stage where it's a collection of like separated problems, almost like silos, and people working on different specialties?
Well, you must work for Autodesk, because that exact problem. So we're a software company, but recently we announced a printer. And for that exact reason is why we decided we're going to enter the hardware world. And so, because really all those things have to work together. And so we put out the printer in sort of like an Android way. Like this is the reference spec. We'll provide the basic sort of underlying stuff for it. But the spec is fully open. People can build whatever printer they want or modify it, etc. So it's very much sort of an open environment for sort of doing that stuff to encourage all that sort of stuff. Because we know that we need, all those parts need to be knowledgeable of one another in order to make things work. Because like there's sort of a joke here that in the manufacturing sector, it's like they assume everything's sort of built out of aluminum or black aluminum or whatever. But what we're finding out with 3D printing is like, well, actually, if you know what the printing medium is going to be, you'll at the front end do a lot more different structural stuff, right? So those sort of have to be known. Yes. Okay.
So some really inspiring stuff in this talk.
Well, thank you.
So thank you for that. And I was wondering, like, as you're building the tools to enable people to design based on various goals, to what extent do you have to actually embed expert knowledge in, like whose algorithms are you gathering, and how much of that do you have to build into the tools themselves to let people just focus on the beauty of the form, or avoid thinking about the shape entirely and just think about the fact that it can self-destruct when it's done with. What kinds of experts are you drawing on for this?
What kinds of experts are we drawing on? Well,
Are you drawing?
Yeah, there's sort of two dimensions to that question. So, what kinds of experts? The people actually trying to manufacture stuff are sort of the experts. Like the classic example I've set up, showing some of our crazy algorithms to people designing airplane wings. They'd go, wow, that's super interesting, but I can't get, FAA approval of that structure ever. Okay, so, and it's simply not the way the industry works. They rely on another manufacturer to get the approval for that way of manufacturing stuff. So there's a lot of different things going on there. But in terms of what algorithms, the one thing that we're just very early into this work, but we are finding out that there's notion that sort of you try different algorithms to get different results and stuff, and we see that in action. Like they'll say, well, let's use classic topological optimization on this versus crazy lattice thing in the lab. So rather than us making the geometry and choosing shapes or choosing algorithms of which ones we think would be more effective, and then lining those up to be evaluated. But like I said, we're in such early days, there's lots of stuff we don't understand yet. We sort of just know that sort of needs to be built, and we'll build it and see what happens.
All right.
Okay, you're going to handle the questions.
I will. Right at the beginning, you had a slide on all the kind of underlying culture of manufacturing and design that needs to change the who, what, where, when, why type of thing. What industries that you're talking to are successfully, or at least attempting to change their culture to go in this new direction? And you just mentioned, the FAA will never approve this, right? So what industries are you seeing are really moving in that direction and looking to embrace this new?
I don't really think of it as industries change. I mean, industries change so slowly that maybe you don't have to worry about that as being sort of the quickest moving part in the scene, right? I think it's more, what sort of entrepreneurs and startup companies we see that are sort of changing the way the major industries work. The classic one is like when we go around and we show the stuff that we're doing in life sciences, we go to a big pharma company they go, "Well, yeah, that's not all that interesting. It's, you know, it's kind of like, well, we need to develop blockbuster drugs. It's just sort of this thing on the side that's interesting, but not the direct target sort of thing." But when you go talk to startup pharma companies, they're going like, "Oh yeah, we definitely want to use the cloud to optimize our drugs. We want to provide a service to the big pharma." So it's a completely different business model.
Right.
So it's almost like, you know, we're in that sort of funny stage where it hasn't sort of hit prime time yet in sort of the industry. I mean, the industry sort of gets, there's probably people from industry here, they totally get 3D printing is for like early prototyping and stuff like that. Only now are people starting to realize that, oh, it's useful for manufacturing in this particular case. And so we're starting to fill in sort of the cases and stuff like that. Now it's going to turn out to be a sort of a very complicated horizon of what is 3D printed and what is manufactured. You can cast mold and all that stuff. But I mean, that's manufacturing. It's tricky, and there's lots of, you know, different cases.
So I'm coming at 3D printing from more of the arts world, specifically in film. And one of the, I noticed that you had an example in your presentation from like a shot from Pirates of the Caribbean and like the
Right.
fully CG printed squid mask sort of thing. And that's like one of the hot discussions in film right now is whether, like, when to go with full CG effects or when to go with practical effects. And there's starting to be more of a push to go into practical effects, such as with the new Star Wars films that are coming out, and J.J. Abrams has announced that, you know, we're going to go with as much practical as we can. And yet I know that there's a lot of the big effects studios in LA are using 3D printing to build prototypes for certain elements in film. But then they use that to make a mold or something like that, and then they use traditional manufacturing techniques to just pump out pieces.
Right.
So given what you were saying about the progression of the design and the maker techniques, do you see the industry getting to a point where, say, that squid character could be produced on a 3D printer and used as a practical effect so that it looks better on camera? Say, as a combination of, say, like your 4D printing, so that the parts actually move. Do you have a sense of where the industry is in terms of that and sort of what needs to happen on the way?
You know, I don't have a sense of sort of where the industry is, but, you know, in terms of the technology, my sense is that, well, that's plastics. I mean, plastics is the easy thing.
Okay.
Because the plastics are so well understood. And so doing things like the mask from Pirates of the Caribbean, I can't remember what the name of that character is now, but I mean, that's, we print stuff not at that scale anymore, but we print stuff that's floppy and flexible and stuff like that. So we sort of got the basic shape going and stuff like that. So maybe there's other characteristics of whether it's toxic or whether it's getting the flexibility. But I really think that's going to be like, we'll go along with it. Yeah, it's used for prototypes, and then suddenly we'll just drop off the cliff where, well, let's just use the damn prototype. Because as you add more componentry, electronic components, and you know, there'll be 3D printers that pick and place electronic components and stuff, and mechanisms and motors and stuff like that. So at some point it'll be like, well, it's prototype, it's fully functional. So I think that that'll probably have a fairly large effect. And it's interesting that, you know, how it sort of competes with CG virtual effects. Yeah. It's exactly what we're seeing in some parts of the manufacturing thing, where sort of the traditional digital process is being a little bit offset by some people saying, oh, we actually print the real part and test it, and we ship that printed part. So I guess the answer to your question is, yeah, I think eventually there'll be lots and lots of stuff that is no longer print prototype, but the real thing. So, Alona?
Some questions over there, behind the booth.
Corey, how commercial has Autodesk taken this? Are we completely down a path where we're offering 3D printers in the marketplace today?
Not quite ready.
Are we headed there?
Yeah, we are definitely headed there, yeah. It's starting off very small, though the Spark printer will produce fairly small pieces, right? But, you know, we announced that we're on that path and we're opening up those specs. It's still a plan that's being formulated and developed over time. But yeah, we're definitely going down that path. Now, we're not going to be, the best analogy, well, not the best analogy, but a good analogy is the Android thing. Google makes Android, right? The operating system for the phone. But the real big manufacturers of the hardware are Samsung and other big phone manufacturers. I don't think we want to get into big hardware manufacturing of 3D printers, but we definitely want to provide all the software and the basic stuff that makes all that stuff work. Because that's the challenge we see, is that unless you fully understand, you know, the entire printing process, the fabrication process, you can't do everything within the digital realm. And so that's really why we're doing it.
That research that's taking place right now within Autodesk, where do we do that here? Do we do it in San Francisco, or do we have it spread around?
Some of it's, most of it's in San Francisco, yeah.
Yeah, go ahead.
Mike,
Oh, you, Richard?
okay. My question is related to the former gentleman there. Is there that open source 3D printer that Autodesk is working on? Is there like a reference design that is operational right now?
Is it operational? I don't know if it's operational yet, but we're definitely doing a reference design where people can get it and, you know, build their own printer, modify it, et cetera, et cetera. Yeah, that's the goal of it. I don't know if it's actually available yet. Do you guys know in the back? Do you know if Sparks?
Might be something uninstructable, just the basics of it, not that the open source.
I don't think it's
That's a good
available.
question, Dave, but the pictures of it look so real because they're computer generated.
Yeah,
Real.
No, I saw it last week, so it exists.
Oh, okay.
yeah, people get a little bit confused about, maybe I'll just, for make it more confusing, but it's not truly open source. Like the Android phone is not open source. You cannot get access, and we wouldn't want anybody to have access to the core code for the Android phone, because then you have these security issues and stuff like that. But there's a very open API, accessible API to do all this stuff. The hardware, I think, is completely open. You can probably download the designs and the CAD files and make the thing print, you know, purple ink with thread in it if you want to modify it that way.
I want to thank you, and I'm wondering, are you curious about the audience? Like, where are people coming from? It would be very interesting to know sort of approximately the space.
Yeah, okay.
But can we go around the room and you just like say the organization that you're from? Would that be okay? Huh?
Sure.
I'll start with, I'm independent and University of Toronto.
A student at University of Toronto, and we're both
Startup?
yeah.
CIBC. Actually from Navrado's lab. that you-
Oh, excellent. Welcome.
Student from Waterloo.
My dad works at Autodesk, but I'm a student at UT.
Great.
Cool.
Former developer, desktop and web developer, now an entrepreneur, robotics and IoT space.
Independent UX.
Autodesk.
CIBC. Independent. We have a small costume and prop company we've been working for 10 years.
Awesome. Together.
Yeah.
Okay.
ULPS/Autodesk.
Okay. Great.
Software industry, old alias user,
Okay.
way back.
Woohoo.
I study at OCAD.
Yeah.
Never really talked to us.
Autodesk. Autodesk.
UBCL.
Retired.
Where? Okay. Yes. You
Autodesk.
guys, Autodesk. Standing in the back, Autodesk. All right.
Supporting board.
Barb.
I'm project manager at the Center for Information Visualization and Data-Driven Design at
York.
CIBC. Autodesk.
U of T?
Yeah, we use the whole together.
All together. Awesome. Were you in my class today? No.
Yeah.
Yeah? All right. Woohoo. See, I told you. I
Wow.
told them to come, and they came. I'm excited. It's going to be a great year.
U of T.
And
User experience at a data analytics firm. Is your experience at an agency? Get your bot on robotics hackathon.
well, thank you all for coming. That was a really awesome. One more hand for Staying and for hosting, and John for doing all the extra. And we'll see you tomorrow at 8:30, right? All right.
Great, thank you.
Thank you.